Here are the two functions we asked you to work with to prepare for this program. We asked you to apply the formula iteration method in each case. Remember, the idea of this method is to find solutions to this equation for each function f. Well, since these functions are quadratic, we could have found the solutions directly without iterating. But we just chose those functions for illustration. Everything that we're going to do in this program applies to more general functions. Now, what we're going to do is to show why some of your sequences converged to a solution and some didn't, and we're going to relate that to those scale factors that we asked you to calculate. Well, let's get started. In the first example, we asked you to start off with x1 equals 0.5, and you should have got convergence. Here we've rounded the values to 3 decimal places. And it does look as if this sequence is converging to 0.1, and in fact, 0.1 is a solution to the equation function x equals x. In fact, when you put 0.1 in, you get 0.1 out. Well, when I did this in my calculator, I got 0.1 to 8 decimal places for x28. So x29 would have been 0.1 as well. But the point is, my calculations weren't exact. If I'd written out all the decimal places, then I would never have got 0.1 exactly. Now, why is that? That's the first thing we have to explain, why we never get to 0.1 exactly. And we also have to tell you why we still say that the sequence converges to 0.1. Well, it would help if we can get a pictorial representation of those iterations. Colin.
Let's start by looking at a mapping diagram like the one we asked you to draw before the program. It shows how the function maps points near the solution. This line on the left represents the domain of the function, and this one on the right represents the codomain. And these lines show how the function maps points in the domain to points in the codomain. Now, the first value, x1, was 0.5, and remember, it was mapped to x2, 0.4. We've reproduced this first iteration underneath. Now, the next value, x3, is f of 0.4, and I could represent the next iteration by a line like this on the same diagram. But there's a clearer way to visualize successive iterates by using a separate diagram for each. What we do for the second iterate is this. We ignore this line, our original domain, and we take this line, our original codomain, as a new domain. And we draw a new codomain over here. And then, if we want to see where x2 in our new domain maps to in our new codomain, we simply slide the mapping diagram over, and then we can see x2 maps to x3. And we just repeat this process for x4, x5, and so on. Here's the line from x2 to x3. Then we take this as our domain and draw a new codomain. And we slide our mapping diagram along to construct the line from x3 to x4, and so on. So it looks like the sequence of points is converging to point 1. But why did Alan claim that you never actually reach point 1 if you calculate exactly? Well, let's look closely at one of the iterations and relate it to the idea of the scale factor. We have a point, capital X, and an approximation to it, little x, with error delta. When we apply the function, the propagated error mu is approximately a multiple of delta, k times delta to first order, where k is the scale factor at capital X, which is 5 over 4 times capital X plus 3/8 for this function. And our solution, capital X, is 0.1. So when you work it out, k is a half. So in our case, mu is approximately a half of delta. The ratio of successive errors, mu over delta, is approximately a half. And that's why you never reach the solution if you work exactly, because each one of these errors is approximately a half of the previous error, the scale factor times the previous error to first order. So you just go on halving your error at each stage, which means there's always a little error left. But why do we still say the sequence converges to the solution? Well, that's because convergence is a mathematical word. And it doesn't mean that you have to actually reach the solution. What it means is that you can get as close as you like to the solution by going far enough along the sequence. And that's true in this case. However close you want to get to the solution, you can get there by halving your error enough times.
So, we got convergence in that case because the scale factor at the solution was a half. And clearly we can generalize this. It looks as if we'll always get a convergent sequence if the scale factor is positive and less than 1. That's because the errors are multiplied by a factor which is less than 1, and so they'll tend to decrease. Well, that's only an approximation, and it only works if the errors are small to start off with. Well, that means you've got to be close to a solution to start off with. The problem is we don't know a priori what the solutions are. I mean, that's what we're trying to find out. Well, there is a secret, and this is it. You've got to draw a picture. So what you do is you draw a graph of the function, and it turns out that where this diagonal line cuts the function, well, that's where you have your solutions. In this case, it would be 0.1 and 0.9. Well, why is that? Well, don't forget, we're trying to find out the values where function x, that's the height here, is equal to x, that's the distance here. Now, every single point on this line, x maps to x, satisfies that the distance here, the height, is equal to the distance here. And in particular, the points where it cuts this graph, 0.1 and 0.9, well, that's going to satisfy that condition, function x equals x. And this is a very general sort of method. All you have to do to find the solutions to function x equals x, draw a graph of the function, and then, if your eyesight's a bit better than mine, you can actually find out where it cuts the graph, and you've got a good approximate solution. And then if you start off your iteration process from there, and if your scale factor there is less than 1, then you're going to get a convergent iteration process. That's because your errors will be small to start off with, and they will decrease by a factor which is this approximate scale factor. So that's how you can use this diagram to get you started. But actually, you can also use this picture to show what happens to the actual iterations themselves. We started with x1 equal to 0.5. Then x2 is equal to f of x1, the height of the graph above x1. And we can put x2 onto the x-axis if we measure its length along the x-axis from the origin. So this point is x2. Notice that the distance x2, measured vertically, exactly reaches the diagonal line. The graph of x maps to x. To get x3, we just repeat the procedure. x3 equals f of x2. And we can measure this length along the x-axis by laying it down and butting it up against the origin. And here's x3. And we can carry on like this. But there's a much easier way of picturing the construction, which we can see if we go back to the beginning. We start as we did before. We get x2 from x1 by going up to the graph. But we don't need to measure this height along the x-axis. Instead, we can just go along to the diagonal, and x2 is vertically below this point. So we know x2 is this length. That is, we can keep a record of x2 by the position of the point on the diagonal. For x3, we can go from the diagonal point down to the graph, and along. And once again, we can record x3 by the point on the diagonal. And we just repeat the procedure for x4. And the same for x5, x6, and so on. Well, we call this sort of thing a staircase diagram for quite obvious reasons. Well, to recap, what you do is you start off with x1 equals 0.5, and then, of course, this distance to the graph is f of x1, which is x2. So this distance, this point on the diagonal, is above x2 on the axis. And then you start your second step here. This is f of x2, which is x3. And so this distance from here, this point on the diagonal, is directly above x3. And then you just continue on down along the staircase down towards the solution. Well, it's quite clear from the geometry of this situation that you're going to go down the staircase, because you always go vertically to the graph, across to the diagonal, vertically to the graph, across to the diagonal, and so on. Well, what about this other solution up here? How are we going to get to this solution 0.9? Well, in the second exercise we gave you, we asked you to start off with a process at x1 equals 1. Clearly the sequence goes miles off. We say it diverges away from the solution.
And that's because the scale factor at the solution 0.9 is greater than 1. In fact, it's 1.5. And the mapping diagram for points near 0.9 looks like this. Here's 0.9, and if I take a point near it, then its image is approximately 1.5 times as far from 0.9 as I started with. So the iteration sequence, starting from x1 equals 1, looks like this.
And here's the corresponding staircase diagram. It's an ascending staircase this time. Vertically from x1 to the graph, then across to the diagonal, vertically to the graph, across vertically, and so on, diverging away from the solution. Well, that's one try, starting with one value near 0.9. What about trying with some other values?
Well, if you take any starting value above 0.9, you're bound to diverge, however close to 0.9 you take it. But what about starting below 0.9? Well, we've seen one example of starting at a value between the two solutions, and the same thing happens if you start anywhere between them. So you move away from the solution 0.9 wherever you start. Here's that diagram again. If you start above 0.9, then you diverge. And if you start below 0.9, then you converge to the other solution. I've drawn a fuller picture here. Here are a lot more iterations. As you can see, if you start anywhere near the solution 0.1, then you're bound to converge to it. And that's because the scale factor there is 1/2. But you can't converge to the solution 0.9 because the scale factor there is bigger than 1. We call a diagram like this a flow diagram for the function.
And each flow line corresponds to a single staircase. Well, both this picture and that flow diagram are useful images to have at the back of your mind when you're doing your little iterations. But the important theoretical result to remember is that if you start close to a solution and you have a scale factor there which is less than 1, then you're going to get a convergent process. Well, Colin showed you that in the flow diagram, but you can also see that sort of thing happening in a picture like this. So remember, in the text, we told you that the scale factor at a point was the same as the slope of a function at a point. So what we're going to do is we're going to consider various functions with various slopes at the point, at the solution, and we see what happens as these slopes become shallower and shallower at the solution. With a curve this steep at the solution, the iterates move a long way away from the solution in just a few steps. We say the sequence diverges quickly. For functions with a smaller slope at the solution, that is, a smaller scale factor at the solution, the sequence will diverge more slowly. Now let's look more closely at what happens when we take functions with slopes closer and closer to 1. The sequence still diverges even though the slope at the solution is less than 1, because in this case we're not starting close enough to the solution. Now let's see a slope of 0.9. And now we get convergence. It takes a lot of steps before we get close to the solution. With smaller slopes, we get close in fewer steps. The convergence is faster. Well, we'll look at negative slopes in a moment. But for now, the message for positive slopes is the following, that if you want to get a rapidly convergent process, then you start off close to a solution, and the scale factor there has to be considerably less than 1. Well, what about negative slopes? Well, in fact, that's what you had in your third example. Here again, we have an iteration process which is converging again to 0.1. But now, we have that the iterations are alternatively below 0.1, above, below, above, below, above the solution.
And that's because the scale factor at the solution 0.1 is negative. In fact, for this function, the scale factor at x is minus 5x. So for x equal 0.1, you get minus a half. The scale factor at 0.1 is minus a half. And this is what the mapping diagram looks like for points near the solution 0.1. If you take a point below 0.1, then it's mapped above, and vice versa. So the error changes sign, and you can see that the distance from 0.1 is approximately halved. In other words, the errors are multiplied by minus a half, which is the scale factor. And the iteration sequence starting from x1 equals 0.05 looks like this.
And so on. We get convergence to 0.1 because the errors are multiplied by a factor of minus a half. So it looks as if we can generalize this idea. We're always going to get convergence if our scale factor has absolute value less than 1. In other words, if our scale factor lies between minus 1 and plus 1. If the slope of the function at the solution lies between minus 1 and plus 1. Well, let's look at a negative scale factor in a bit more detail using this function that we've just seen. Remember, the solution again is given precisely where this diagonal cuts the graph of the function. And we start off at this value of x1. So this is f of x1. And let's see what the iterations look like. Well, this time we actually don't get a staircase. We get something that looks a bit more like a cobweb. We measure the distance x2 horizontally from the origin. And, as before, the distance x2, measured vertically, exactly reaches the line x maps to x. Then x3 is f of x2, and we measure it horizontally from the origin. So x3 is this distance, and we can record its position by the point above it on the diagonal. In the same way, we could have recorded x2 and even x1 by the points on the diagonal above them. So we have x1, x2, and x3, and so on. So just as with staircases, you always go vertically to the graph, across to the diagonal, vertically to the graph of the function, and so on, right towards the solution. Well, let's see how the cobwebs change when we look at functions with different negative slopes. For small negative slope, we get very fast convergence, but the convergence gets slower for curves which are steeper than this at the solution. With a slope of minus 0.9, it takes a tremendous number of spirals before we get near the solution. But now, if we take a curve which is slightly steeper than slope minus 1, we get divergence, slowly. For curves which are even steeper at the solution, the divergence is faster. Well, that just about covers all the cases, and we've summarized them by these pictures. When you've got a scale factor which is greater than 1, then you're going to get divergence. And when your scale factor is less than 1, then you're going to get convergence, provided that you start close enough to your solution. Well, the question that you're probably thinking about is, what do I do if my scale factor is not less than 1? Well, there's nothing for it. You'll have to make some rearrangement of your equation. But we're not interested in that aspect of it in this program. What we've been concerned with here is how you actually go about implementing a given formula iteration method and how you can predict whether you're going to get a convergent sequence or not. And the message has been, you draw a graph, you find an approximate solution, and if your scale factor near that approximate solution is less than 1, then you're going to get a convergent process. And in conclusion, remember that by convergence, we don't mean that you're going to hit the solution exactly. What we mean is that you can get as close as you like to your solution by going far enough along the sequence.